Buenas, ¿qué tal?
Hi, how's everybody? Pleasure to have you. I'm Agustin Huerta. I'm the Senior VP for Digital Innovation in Global. I'll talk about quantum computing. But before that, I will thank the interpreters. I will thank them and I will apologize because I won't make their job easy. Having said so, I will start. Yesterday, Nico Hodal said, "What's next?" And this year we talked about AI. 2024 will not going to be the quantum computing year, but this is coming in the near future. And I would like to travel in time. I'll go to history to refer a story. You heard about the Gordon Moore's law. In 1965, he said that approximately every 2 years, 18 months or 24 months, the number of transistors inside a processor will modify, will duplicate with minimum changes in the cost. For this to happen, it was important to start reducing the size of the transistors. Today, and a very short while ago, we talked about a 3-nanometer process, which allows us to put more transistors into the chips. And there are differences in size even, because it's difficult to accommodate more transistors in small units. Some people are analyzing, instead of modeling a 2D space, I will use a 3D space for the transistors so that I can have a reduced space. This helps improve the energy efficiency, dissipation of heat, and so on. But nanometers that seem to be so far away from us pose challenges. Today's processors are made of silicon. They are silicon processors. So this component, the molecule of silicon, has a certain width. And if the material is smaller than that, it cannot be used. So we have another greater challenge, which comes from physics. What happens if we get closer to 0.1 nanometers, or we talk about a different unit called angstrom? I apologize to the interpreters. We leave the classical mechanic realm, the physics as we understand it, which explains what we see at the macro level, the gravity law. If I push a ball against the desk, it will rebound. And then we enter in the quantum mania, the quantic world. What happens in the world of quantum? Rules change. If I throw the ball, there is an effect called tunneling, which makes it carry on or rebound. So what's interesting about all these rules is that we understand them when we observe them, but we do not have the mathematics to really explain the behavior behind them. But we do know that we won't be able to operate as we are doing today. So we are on the verge of a change. Will technology allow us to go on as we did so far? I will talk about more nerd-based things. This is a challenge to get to these very small units of measuring and the processes that processors undertake. We are getting to the limit. The power of lasers is inefficient to create the chips. Then we'll have X-rays, and X-rays, due to their bandwidth, have a special thickness. And this 0.1 nanometer is making the picture more difficult because the X-rays, which are very close, are close to the limit as well. So when we go into the quantum world, we started defining things like, well, maybe we could use certain principles of the quantum mechanics to modify the way in which we did or thought about systems, the logic behind the systems. And when we abandon the world of transistors and we start talking about atoms, subatomic particles, and so on, we no longer talk about bits and we talk about qubits. The bits represent information, the form that we've been using for a long time, and it has two states, 0 and 1, and that's it. So all we try to represent in the world, all that operates in our daily world, are based on zeros and ones. But how do we represent certain types of information? That's complex. We've been able to handle more bits, to store more bits, and we have increased the storage capacity, processing capacity. We've been talking about artificial intelligence, and this depends on increasing the computing capacity. Obviously, there is a consumption of resources to get to that point. The qubits, contrary to the bits, are represented as spheres, the block spheres. In the block spheres, we can represent information using coordinates within the sphere, so we can storage more states. This brings difficulties because the qubits belong to the quantum world and they suffer when they are being observed. We alter their quantum state when we observe them. If we try to measure them, they will be affected. That's part of the noise that may lead them to mute or change their quantum state. This can be interpreted in many different ways. One is called the Copenhagen interpretation. A physicist called Schrödinger has a principle which rules in the quantum mechanics, which is called superposition. Schrödinger tried to explain that with a paradox, where he said, if we put inside a box that will have a flask with a poison and an isotope, and we put a cat there. If the radioactive isotope breaks the flask with poison, outside of the box is black. We cannot see whether the cat is alive or dead. So the cat, at some point, for the observer, is alive and dead at the same time for the observer. If I open the box to observe the cat, that disappears because I will see whether he's alive or dead. So a superposition has to do with that and the quantum states. So this makes it very, very hard for us to understand. In the browsers today, when we try to explain in YouTube videos, everybody tries to explain the quantum computing. And to be honest, it's very hard to understand how all this operates. And more than one of us have been able to interpret how our cell phones or computers operate. I'm convinced that maybe if we go down to the basics, we may be losing sight of what is important. What will quantum computer change? How useful will it be? So I will make a dream come true. I will become a chemistry professor. Well, let's talk about basic chemistry. There's a disclaimer at the bottom. It says all the values I will show are merely approximations. There are infinite ways to estimate this depending on how complex is what I want to represent. So if you know more than I do about quantum computing, please accompany me in this endeavor. And maybe if the figures are not very accurate, they will help me explain my point. Our chemistry class will start by looking at the hydrogen atom, which is very basic. It's made up of one proton and one electron. And that's an atom, an isolated atom that will help us create molecules, like the hydrogen gas molecule. To represent a hydrogen atom, there are different variations, but we need 2 qubits. There's no other way in which I can explain how many bits are represented in one hydrogen atom, depending on what we want to represent. So we have experienced a lot with the hydrogen molecule, which has 2 hydrogen atoms. And we need about 10 bits to represent that hydrogen molecule. But if I go into the qubits world, I need 4 qubits. So there are very few ordinals of difference.
Right, let's play a little bit more with chemistry. Go from hydrogen gas and we'll move on to water. Water has 2 molecules of hydrogen and 1 of oxygen. Hydrogen is a bit more complex molecule. It has something like 10 electrons and protons, roughly. Now, to represent the same stage that I was representing, I would need 1,000 bits, but only 14 qubits. So we're going to see interesting differences here. And now I'm going to make it a little bit more complex, and I'm not going to talk about basic chemistry. Let's leave it out. And we're going to look into a molecule to which I'm very thankful, because I woke up at 2:30 in the morning, so coffee is going to be a big ally. And this caffeine molecule, forget about 1, 2, 3 lexics. I'm sorry, the interpreters. This is far more complex. We have hydrogen, oxygen, you have nitrogen, and you have carbon. Now, to represent this molecule, we need 10 at 48 bits. To give you an idea, it's a 10 with many zeros. I don't even know the name. And so we go to the field of teras, and then it's 10 at 48. But it's 10 at 48 bits, or this number of bits. Now, we can't even store it or workable or processable. So we either simplify the representation of the molecule of caffeine, and we start losing part of that information to work with it, or we can go to the qubit kingdom, and we'll probably need 160 qubits. I haven't invented this example. It is taken from a book called Dancing with Qubits by Robert Sutton, to explain as easily as possible these capacities that we have to store information thanks to the capacity of qubits. Now, why have I done all this? So that you can understand that this form of representation, some of the fields will be able to analyze with them. And I would like to go a little beyond that. We do have processors for 160 qubits, roughly. But the world of quantum computing isn't that simple. You can have 433, or even, if it was announced, next year we're going to have processors of 1,000 qubits or more. We suffer many things, like the error rate in readings, or the fact that we haven't got 160 qubits to be able to use them for everything. So right now, it's a bit far away to represent this molecule correctly. And in fact, some of the most recent papers, there is one, if I'm not mistaken, from May this year by IBM, where they published a paper how to use their SDK of development to represent a hydrogen molecule. 4 qubits. Their processors are 400, can process 400. Just to mention that the number of qubits may seem a lot, but we're far away to turn them into something easy, and even with a level of abstraction. So to get to quantum supremacy is complex. We've been developing for a long time. The first computer tested with 2 qubits was created in 1998, and even today we have problems to deal with that number of qubits. But let's think a little bit about the use cases that can measure quantum computing. If we can work with molecules of different types, we could do it to develop new drugs, perhaps to find a drug that can help us heal and cure cancer. And we could use quantum mechanics for that representation. But if we also think how we're going to take care of this planet, how we are going to continue developing as a society, how we're going to develop things that can allow us to get to the space more easily. In the world of molecules, we can work with new materials or materials that haven't existed or that we hadn't had the idea of how to combine them at present. Another interesting problem that we can develop with this is fraud detection, and we're moving into finance here. The challenge now is not only the computing capacity that we've got, but that it's so limited that we wouldn't be able to do this in real time. And what is it that you are looking for when you are doing this fraud detection? Well, you want to do it as quickly as possible, but it's a field where we could use it. And once we have autonomous cars and 5G working fully, and so that those cars can work fully on AI, we could solve, for instance, the question of traffic and routes using quantum computing to find out optimum roads. Now, many of these things are already being done with an ally, which is AI. We've been talking a lot about AI in this event. And so the idea there is that it's a place that's going to be optimized, improved with new possibilities thanks to quantum computing. Now, we do have to have clear in mind that it's not all types of AI or algorithms or models of AI, because there are operations for which quantum machines aren't the most efficient ones. But these are just a few, and it's just an overview, and many of things that we are doing research, high papers, there are papers, there are people trying to get the algorithms being used at present to develop new drugs to quantic or circuits or models. The way of programming is different. But, well, every technology has other areas that we have to take into account. And one of the problems that we are faced with quantum computing is that it's a risk for cybersecurity, as we know it now. Many of our algorithms to secure and encrypt information depend on operations that we understand are very complex, because of for a computer with a binary logic. A long time ago, an algorithm was developed to test these machines that allows us to speed up the factoring of premium numbers. And let me explain to you why. This is a key to be able to disentangle the secret passwords with which we generate encrypted passwords. And that's no longer a secret, and it could be disclosed. But we are far away from that, because to be able to solve an RSA of 2048 bits in a reasonable time, let's say 6 to 8 hours, we have to have thousands of qubits that can really be used. So we're a bit far away. But there is a possibility for information to be stolen, with making a security breach. Someone is observing some operations, and we think that it's secure for the next 30 or 50 years, and we can't ensure that in that time we're not going to be able to discover something that transforms the challenges that we have now for quantum computing. For instance, that we have a superconducting material, and to have conductivity, we have to get closer to an absolute zero temperature. A few months ago, a paper appeared saying that they have found an element that could act as a superconductor at room temperature. Unfortunately, that wasn't the case. But if that was the case, the concepts of what we think can be done with quantum computing could change a lot. So this isn't catastrophe, but we have to start thinking right now that this is a possible risk. So I'd like to conclude, to go back to a question that Nico Hodal said, what's next? And I would like to take a step forward because I'm talking about GX30, and I dare say, why is it that Agustin is talking about quantum computing? What has this got to do with GeneXus and GeneXus Future? We love to dream with Gaston, and unfortunately for him, from time to time, he gets a WhatsApp from me with one of these flying crazy ideas that I've had. So about 3-4 weeks ago, I told him, Gaston, yesterday I was discussing quantum computing, and I think that we have to think that if GeneXus ensures not the eternal youth for the code or for system modeling, and then with the code and representation and information that it must have, why can't we think that we can also make codes and the data that we generate through GeneXus are post-quantum ready? Because all this question of encryption is true, but there are already algorithms of post-quantum encryption using other techniques to ensure and secure those scripts. There is a principle in quantum mechanics called interlinking, quantum interlinking. I can make all atoms to be related and their status the same. Now, if I have that object to control the interlinking, no one else will be able to replicate those two copies in exactly the same status they had. And that's the way the networks will develop to transport quantum information. So, for instance, the U.S. government, in one of its initiatives, has already established that all tools used to build systems must have, in 2 years' time, the capacity of a post-quantum encryption, and they expect that by 2030, all their systems will have migrated and work with this type of algorithms. Why can't we build now systems with GeneXus that the only thing we have to do is to change a couple of variables and they are ready without having to go through an extensive and complex, painful process of 10 years or 6 years or whatever to migrate those solutions? This is the end then. I would like to make you think and dream, and thank you for your patience and your time. And thank you. Thank you, the interpreters who have accompanied. I'm sorry if I made your life difficult. Thank you.